Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University, Gwalior. Today, in this lecture, we shall study Electroanalytical Chemistry Part 1 under the paper Fundamentals of Analytical Chemistry. Learning objectives today are how electrochemical reactions take place. I can say here that electroanalytical or electrochemical techniques involve the movement of electrons, or we can say transfer of electrons from electrode to solution or solution to electrode. It is charge transfer of electrons. Here, as in the case of spectroscopy, you have seen that energy is being provided with the help of electromagnetic radiations there, and we provide the energy, electromagnetic radiation, and we measure the absorption or transmittance. Here, we provide energy in the form of potential and measure the current. What is the effect of energy and on the solution, and we measure the current. And the electrode functions as the source of electrons. When an electrode is negatively charged, means it contains excess of electrons, and it is called as cathode. When an electrode is have deficient electrons, a deficiency in electrons, it is positively charged, it is called as anode. So overall, in an electroanalytical technique, it involves the transfer of electrons from one place to another. A very, very simple technique, very fast technique. It is a group of different types of techniques. What different parameters are involved here in? What manipulations, combinations we can do is only three things: current, potential, and coulombs. We may increase or decrease the potential and may see its effect in the form of current. We may provide different amount of uh, uh, current, different amounts of current and measure, and we may see its different effects. Or we may say that we may consider it a solution as a black box, or an electrochemical cell may be considered as a black box in which two electrodes are there. For finding out the nature of the substance present there, nature of the solution present in that black box, we have excite the system. We have to perturb the system. How to perturb the system? That we shall apply some energy. Here in electrochemistry, we provide energy in the form of potential. We will provide energy, and then we shall study the outcome in the form of its current. Due to relative inertness of water and high dielectric constant, it is the most satisfactory solvent, although many organic solvents have also been used successfully. By far, the most common use of electrochemical cells in chemical analysis is the determination of the concentration of one of the species in a solution. For example, the determination of hydrogen ion with the pH meter. There are many ways in which an electrochemical cell can be constructed and operated, giving rise to a group of techniques for special purposes. Some of the important analytical techniques are the potentiometry. In this technique, the potential of an electrode is used to measure the concentration of a given species in a non-reacting system. Another technique which is the modification of potentiometry, is potentiometric titration. Here, the concentration of a given species that changes during a titration is measured by potentiometry. Another modification of electrochemical techniques is electrolysis, in which the amount of a substance present is determined by reducing or oxidizing it at an electrode, measuring either changes in weight of the electrode, that is the electrodeposition, or the number of coulombs required to complete the reaction, which is called as coulometry. Coulometry is an electroanalysis. In other words, coulometry is an electrolysis which is performed at constant current or with one of the electrodes at a fixed potential and the number of coulombs measured. Actually, in electrochemical techniques, technique depends upon the electrochemical parameters, where in some technique we keep the potential constant, somewhere we keep the current constant, somewhere we measure the time. So it depends upon that. Next type of the technique is voltammetry, in which an electrolysis is performed in an unstirred solution and the current is measured as a function of the applied potential or vice versa. So a sub branch of voltammetry is polography, in which we take, instead of a solid working electrode, we take dropping mercury electrode. So wherever in voltammetry the term polography is used, it means that our working electrode or indicator electrode is a dropping mercury electrode. The next technique which comes under electrochemical techniques is chronopotentiometry, in which an electrolysis is performed in an unstirred solution at constant current and the potential of an easily polarized electrode is measured as a function of time. After that comes another technique known as conductometry. Here, in conductometry, the electrical resistance of a solution is used as a measure of the total ionic concentration in the solution. Although some of these methods can no longer be considered modern, applications in the areas of organic chemistry, biochemistry, and pollution monitoring continue to increase, and these techniques are still used. So, for applying any modification of the electroanalytical techniques, one fundamental requirement is that we should have an electrochemical cell. What is electrochemical cell? Electrochemical cell consists two electrodes. One is working electrode and another is reference electrode. And these two electrodes are dipped in a solution which is to be electrolyzed. For example, the reaction between zinc metal and ferric ion is a typical redox reaction which can be carried out by dipping a piece of zinc metal in a solution of ferric ion or by setting up an electrochemical cell as shown in figure 1, in which this reaction takes place. One half cell contains a solution of zinc salt and a piece of metallic zinc. The other contains a solution of ferrous and ferric ion and a piece of platinum metal that serve as an inert electrode to supply or withdraw electrons from the solution. Here, these are the two electrodes, reference electrode and one is the working electrode. And working electrode is a source of electron or it takes out electrons, and the reaction is called as oxidation or reduction, as the case may be. When electrodes supply electrons to the species, it is the reduction. When it takes out electron, it is oxidation. In this electrochemical cell, as you can see in figure 1, the zinc half cell, zinc metal may dissolve as zinc ion, leaving the electrons behind to give the electrode a negative charge, that is, excessive electrons are present on the electrode surface. Alternatively, zinc ion may deposit as zinc metal on the electrode, causing a deficiency of electrons on the electrode. For a given concentration of zinc ion, an equilibrium solution is established with a resultant charge on the electrode. Likewise, in the ferrous-ferric half cell, ferrous and ferric ions can exchange electrons with the platinum electrode, establishing an equilibrium and a resultant charge on the platinum electrode. As you can see in figure 1, the charge on the zinc electrode is more negative than the charge on the platinum electrode. If the two electrodes are connected with a wire, electrons will flow from zinc to platinum and the reaction just described will occur. However, we cannot increase the concentration of zinc or change the initial ratio of ferrous to ferric ion without disturbing the electroneutrality of the solutions. Since we cannot accumulate electric charge in either solution, the reaction cannot continue unless we provide a mechanism for transferring ions from one half cell to the other. The salt bridge serves this function by allowing a small ion current to pass from one half cell to the other in either direction with only negligible mixing of the two electrolytes. When this cell operates spontaneously, as you can see from figure 1, here number of phenomenon occurs. Number 1, zinc metal is oxidized and dissolves. Electrons are transferred from the zinc electrode to the platinum electrode through the wire. Number 3, ferric ion is reduced by the electrons on the platinum electrode. Number 4, cations migrate from the zinc half cell to the ferrous ferric half cell through the salt bridge. And the last, and anions migrate in the reverse direction. By means of appropriate switches and resistances in the external circuit, we can start or stop the cell reaction or control its rate. By means of appropriate meters, we can measure its rate and the driving force. The operation of a cell clearly requires a chemical reaction to take place. Thus, the concentration of the various species will necessarily change with time. For the most part, we will be concerned only with the cells in which no current is flowing. It is important to note that the charges on the electrodes are the result of chemical reactions. However, the amount of chemical reaction required to establish the charge is so slight that it cannot be measured and is safely neglected when compared to the total material in the cell. For example, we can understand it by saying that a free charge of 10 raised to power minus 17 mole of electron will cause a potential of 1 volt at a distance of 1 centimeter. In these non-operating cells, we shall assume that each half cell reaction is in equilibrium with its own electrode. A difference in potential between two electrodes implies that the two half reactions are not in equilibrium with each other. In fact, the potential difference measures the force tending to drive the system toward equilibrium. So, if I consider an electrochemical cell which contains one anode and one cathode, or I can say one reference electrode and one working electrode, then there are different types of electrode which we can take. We can take different types of working electrode, some of which I shall discuss here. A half cell is designated by listing the species taking part in the half reaction, separating the electrode from the electrolyte by a vertical bar. For example, I will illustrate some of the conventions. Here, metal-metal ion, in which the metal of the electrode takes part in the half reaction. As shown in figure 1, it is represented as zinc bar zinc ion. Zinc ion here is 2 ions are there, the zinc plus 2. Means we will represent the cell, half cell as zinc bar zinc plus 2. And in the another case, if suppose there is a metal complex, then metal dash complex in which an excess of the complexing agent is added to regulate the particular form of the complex, then it will be presented as, if we have taken here the copper ammonia complex, copper wire, copper, ammonium ion plus 2, ammonia in correspondence to ammonia. This is the, as you can see here, this is the representation of the half reaction, how half reaction is represented. In another case, if we take silver chloride electrode, then metal saturated solution of one of its salts in which the presence of the solid salt is inconsequential except to ensure that the solution is saturated, and it is represented as silver silver chloride in reference to chloride ion. In case of gas ion, in which the solution is saturated at a given pressure with the gas as it is bubbled over the surface of an inert metal electrode, it is represented as platinum hydrogen hydrogen ion or protons. Ion in which both the reduced and oxidized forms are soluble in the electrolyte, and an inert metal electrode, as we have taken here platinum electrode, is used to make electrical contact between the electrolyte and the external circuit as shown in figure 1, platinum iron 3 in reference to iron 2. Amalgam ion in which a reactive metal is amalgamated so that direct chemical reaction with solvent is minimized may be represented as sodium amalgamated with mercury sodium ion. Finally, if two half cells are combined to make a whole cell, the electrodes are listed first and last. For example, the cell would be represented as zinc electrode, zinc ion, double iron plus 3 in reference to iron 2 platinum. On both the sides are electrodes. On one side it is working electrode and on another side it is reference electrode. The double bar signifies the salt bridge between the two half cells. So now you have understood what are half cells, what is the representation, how we can connect two half cells. We connect two half cells by a salt bridge represented as double bar. Unless otherwise indicated, the solvent is assumed to be water and not listed as one of the cell ingredients, even though it may take part in the reaction. Insofar as practical, we shall write the predominant form of a species in the solution. For example, iron plus 3, iron hydroxide, iron chloride plus 2, acetate ion, etc. The charge of an electrode results from an excess or deficiency of electrons on the metal. A large negative charge indicates the presence of a strong reducing agent, that is, good electron donor. The potential of an electrode is defined in an electrostatic sense. The absolute electric potential of a point is defined as the work needed to bring a unit of positive charge from an infinite distance in space to the point in question. The potential difference thus compares the charge existing at 2 points. In relative measurement, we often use the term potential of an electrode when we mean potential difference relative to an arbitrary standard difference electrode. Likewise, a cell potential really the difference in potential between the two electrodes and is more properly called the cell voltage or electromotive force, and it is designated as E cell. The charge of an electrode, the electrode potential, the difference between two electrode potentials, and the direction of electron flow in a wire connecting the electrodes are all physical facts independent of any arbitrary sign conventions. Here we shall use following rules. Number 1, the potential of and charge of an electrode and driving force of the corresponding half reaction have the same numerical value and sign. Thus, the electrode potential designated by the symbol E is also a measure of the charge on the electrode the tendency of the system to accept electrons, that is, its power to oxidize some other species. E for an electrode or a half reaction is compared to and measured relative to E for the standard hydrogen electrode SHE to describe shortly. In every cell, one electrode is arbitrarily designated as the left electrode EL and the other electrode is represented as right electrode ER. The cell reaction is obtained by subtracting the left half cell reaction from the right. It should be evident that the cell reaction cannot produce or consume electrons. It can only transfer them. If the number of electrons n is not the same in the two half reactions, one or both half reactions must be multiplied by a suitable factor to cancel electrons. Cell voltage indicates that the cell reaction proceeds simultaneously in the direction written. The right electrode has a more positive or less negative potential than the left. Reduction occurs in the right half cell and the oxidation in the left when the cell operates simultaneously. Electrons flow from left to right in the external circuit. A negative cell voltage corresponds to statements opposite to those just given above. In the discussion on Nernst equation, we have assumed that system behave reversibly. Reversibly means if we reduce the substance and product is formed, then we oxidize the product, then the same product should be formed which we have taken. For example, if we take a substance A and we reduce it and it forms B, then after oxidation and applying the same potential, it should form the product again A. Such systems are called as reversible systems, and that has been assumed in the discussion of Nernst equation. But sometimes the process is slow. The process is slow due to the various factors, due to the electron transfer from the electrode surface to the solution or from the electroactive species present in the solution to the electrode surface. Actually, while transfer of electrons is taking place from surface of the electrode to the electroactive species present in the solution, means to the analyte. It is very important to understand that electron transfer is taking place from the surface of the electrode or from the analyte or electroactive species to the surface of the electrode. One time it is oxidation, another time it is reduction. So, if that process is slow, transfer of electrons is slow, then the process is irreversible. It will not follow the Nernst equation, and there will be difference of 0.059 upon 2 volt. It will be more than that, and process will be called as irreversible. So while in discussion we have assumed in Nernst equation that it is a reversible process, but when the process is slow, then the process becomes irreversible. In electrochemical analysis or electrochemical cell is formal potentials. Many redox reactions involve species other than those between which electrons are transferred. For example, many oxidants contain oxygen, requiring that hydrogen or hydroxyl ions and water appear in the reaction. In other cases, complexing agents may be consumed or released. Consider, for example, the reaction between copper 1 and permanganate in hydrochloric acid solution, where, as you can see in the equation, chloride anion, copper chloride, manganese ions, all are required here along with water molecules, and here we can say that a cell reaction is written as half cell potential, which are written as separately, E representation for manganese separately and copper separately, as you can see from equations 11 and 12. where we have applied Nernst equation. Here Nernst equation has been applied and we have taken oxidation number for both the cases. When we use this reaction, we employ an excess of hydrochloric acid and its concentration stays relatively constant as the reaction proceeds. Under these conditions, protons in equation 11 is a constant and the long term can be separated and we obtain equation 13 and 14 as you can see here, and equation 13 and 14 define the formal potential E dash for this couple. E dash is a constant which has a different value for each concentration of hydrogen ion. E dash can be described as an effective or practical value of E0, and in this case it is seen that E dash becomes more positive by 855 into 0.059 volt as proton is increased tenfold. Thus, changing the pH is a simple and powerful means for changing the oxidizing or reducing power of a reagent. This is a common situation for many inorganic and most organic reactions. The same argument can be applied to define a formal potential for the copper half cell, which includes the effects of the concentration of chloride ion as shown in equation 15 and 16. Formal potentials include the effect of ionic strength, complexation, hydrolysis, the effect of pH, and any other effect which can be attributed to the composition of the electrolyte other than the ratio of the reduced to oxidized form. Electrodes, which are used in an electrochemical cell, are of two types. One is the working electrode or indicator electrode. At indicator electrode, we apply the potential and its potential changes as we apply. Another is the reference electrode whose potential remains fixed. When we apply certain potential, its potential will not change. Not change. So different types of reference electrode that has been used are hydrogen electrode, quinhydron electrode, smooth platinum electrode, calomel electrode, and silver chloride electrode. The most commonly used electrodes are calomel electrode and silver chloride electrode. Here in calomel electrode, a saturated potassium chloride solution is taken and it is prepared, constructed, and it can be constructed very easily in the lab. Its potential remains constant and we measure the potential of the working electrode in reference to the saturated calomel electrode which we have taken. Similarly, we can also take silver chloride electrode. Its potential remains fixed. It is a well-known potential of it, and in reference to that, potential of the indicator electrode is measured. Indicator electrode may be of different types. It may be a solid electrode. It may be a dropping mercury electrode as we take in case of polography, or it can be a membrane electrode which can be taken as in the case of glass membrane electrode, which you have studied in place of pH meter, where working electrode is a membrane of glass membrane electrode is used as an indicator electrode. For the measurement of cell voltage, ordinary voltmeters and ammeters require small but appreciable currents to deflect the needle. Since any current flowing through the cell will necessarily change the concentration of the reacting species, the simple voltmeter is not a suitable device for accurately measuring a cell voltage. Two alternatives are available. One is the electronic voltmeter. For this purpose, a high input impedance vacuum tube voltmeter requires as little as 10 raised to power 14 ampere current to give an accurately measurable reading. Modern meters are transistorized and require a negligible amount of power from the source to be measured. In the potentiometric circuit, the voltage to be measured is exactly balanced by a known variable voltage as shown in figure. The accuracy of determining the null point is limited by the current necessary to detect the off balance. The use of high impedance voltage amplifier in a potentiometric circuit provides the ultimate accuracy in voltage measurement. The half reactions are always at equilibrium with the corresponding electrode, but the overall cell reaction in general is not at equilibrium unless the cell voltage happens to be zero. Under the latter condition, the ratio of activities of products to activities of reactants must satisfy the equilibrium constant K for the cell reaction, and the following equations apply well, which is shown here. E cell is equal to E0 cell minus 0.059 upon N log of products upon reactants. A very important reaction which will apply here, and here equilibrium constant is the factor which should be applied. If we solve it, then after solving it comes to log K is equal to N E0 cell upon 0.059 at 25 degrees centigrade, where E0 cell and K must correspond to the same reaction. If E0 cell is positive, then K is greater than unity and vice versa. To avoid confusion over signs of E0 values, remember that half reactions should be subtracted in a direction to give the required whole reaction, and the E0 values corresponding to these half reactions must be subtracted in the same direction. So in this lecture, students, you have studied about the fundamentals of electroanalytical techniques, and you must have appreciated that the techniques which you have seen here are very simple, very fast, and easy to do in any simple laboratory. What is there in electroanalytical techniques? If we say in a sense, it is the movement of electrons. From where movement? Remember, the place from where movement, electrons are coming. Electrons are coming or going to the electrode surface. From where it will go to where it will go? It will not go to the solvent. It will not go to the solution. It will go to the analyte. For example, if I take cadmium ions, so cadmium ions are present in the solution in the form of cadmium 2 plus. These ions will get deposited at which electrode? It will get deposited at which electrode? Which are having axis of electrons. Means it will go to the cathode, and it will take electrons from the cathode because at cathode axis of electrons are present. Similarly, if I take cadmium metal, then it will go, if it is oxidized, then where oxidation will take place? Where oxidation will take place? At the anode, because anode is electron deficient. It will take electrons from the cadmium and convert it into the cadmium 2 plus ion. So important thing in this lecture, which I am again and again emphasizing, that in this electroanalytical chemistry, it is the transfer of electrons from or to the electrode, from or to the electroactive species. The technique is simple, very fast, no complications are there. Only thing to appreciate that it is the electron transfer and reactions are taking place. We are measuring these. What may be the different applications of these techniques? The applications involve study of kinetics of the reaction, study of thermodynamics, study of finding out the intermediates involved in the reaction, what are the intermediates, to find out the end product for electroorganic synthesis, to find out the unusual oxidation states of metal, to stabilize the unusual oxygen states of the metal. So there are, in each and every field of chemistry, electroanalytical techniques find applications. Thank you.